1D analysis for marine application. Modeling of ship in GT Suite for evaluation of performance parameters. Abstract. The performance of a ship vessel is very important in deciding the kind of engine, turbine, thrust force, and importantly the launch speed and cruising speed matching. There are different approach for the same, and one of the approach is to define the same by 1D model approach. 1D model gives flexibility in analysis also with approach for solving complicated equations. The results can be correlated with that of test results and modifications can be done in model. This will give necessary flexibility in designing new ship and its requirements. This work is divided in different steps. First step involves modeling the ship in GT Suite, which is the first time activity. Second step involves the correlation of the 1D model with the real case scenario. Main output of this analysis is knowing the proper engine size for the required thrust of the ship. This was done by studying the parameters like ship speed, engine speed, fuel consumption, clutch engagement and disengagement, power, torque, distance traveled by the ship. Keywords: GT Suite, thrust, torque, resistance, propeller pitch. Introduction. Virtual calibration is picking up its pace and used extensively in all new fields. In current world, the simulation technique is used extensively from AI to calibration. This will help to carry out multiple iteration and to arrive at an optimum solution. With 1D and combination of 3D CO simulation, the solution will be near to perfection and multi-variables can be analyzed. One such field where 1D model development is associated is in marine section. Greaves has its own marine division and it's aiming to supply world-class product to end customer requirements. The key aspect ship modeling is the behavior of the propulsion system, which is the crucial part while designing and optimizing it. Generally, this analysis has to be done in transient condition, which can predict the acceleration, deceleration, turning events where the propulsion system is tested to its limit. In present paper, the ship is modeled with the help of 1D tool GT Suite. This is done by vast library present, which can be used for building the initial blocks and defining the equations and then integrating these blocks and equations to replicate the ship model, which would predict the performance of the physical ship. As ship can be considered similar to the on-road vehicle except the medium on which it is driven, so most of the GT module which can be used for the vehicle modeling is used and the remaining part is modeled in the form of different controllers. Current analysis is to propel a ship of 32 tons weight and to use the current engine with combination. Dual 4-cylinder engine delivering power of 170 HP at 2000 rpm is modeled. The output of the analysis is correlated between test and the virtual simulation for ship speed in transient condition, distance traveled. 2. Literature study. This is an important step and this will give us a window of knowledge on how other team is progressing in this field. Some correlation can also be done with reference to physics of problem. M. Figuri and M. Alto Sol 1 has analytical study where they predicted the performance using analytical equations. According to them, model including two nonlinear differential equations of motion representing ship dynamics and propulsion plant dynamics was built. Paper shows that a ship with a GT propulsion plant and with a humped resistance curve has two types of behavior, a stable behavior and an unstable behavior, depending on the speed range. The presence of an unstable working range presents a concern from the system design point of view. Hyun Wang, Huiyin Tang, Jian Hui Sun too also performed the modeling and simulation for ship maneuvering condition. The dynamic simulation models of propeller running across 4 quadrants and ship longitudinal motion were given. The model concerns in all working conditions, including starting, braking, reversing, etc. Combination simulating of diesel propulsion system and ship motion was conducted. Difference between residuary resistance simulated and real residuary resistance, there were relative errors. Tom Trent-Tellman, Joshua Sutherland, Kazuya Oishimi, Kazuhiro Aoyama 3 describes a method for early-stage boat design by creating and utilizing a library of naval architecture based boat components in Modelica. Even without detailed domain knowledge of naval architecture, a user was able to assemble and compare different models. By using Modelica's object-oriented features, the methodology enables radical or minor changes to a simulation model with one mouse click. With the possibility to directly run a 3D animation of the simulation model, the reaction to these changes can be reviewed immediately. 3. Ship modeling and equations used. Model architecture is same as the basic vehicle architecture. Instead of vehicle, ship has been modeled to follow the basic concept of marine engineering. Model has been made by using various equation for the thrust and torque, which will be used to calculate the boat velocity and distance traveled. Equation used for the modeling are: effective thrust is given by Tp equals kt.n2d4. Effective torque is given by Qp equals kq.n2d4. Here thrust coefficient kt and torque coefficient kq are functions of the advance coefficient j and propeller pitch, or pitch diameter ratio. Coefficient j is calculated as Va/nd. Generally, this should be available from the open water propeller test, but here as the testing data was not available, so the value taken from the literature example, where Tp equals propulsor thrust, n. Tq equals torque, n. Kt equals thrust coefficient. Kq equals torque coefficient. N equals shaft speed, r/min. D equals propeller diameter, m. Va equals advance velocity equals v, 1. M/s. Equals sea water density, kg/m3. Once the ship has been dynamics has been modeled, next part is velocity and distance calculation. This is calculated from the available thrust, resistance, and mass of the ship. We know that force equals mass * acceleration. Acceleration equals force/mass. Force equals thrust resistance. Resistance is available for the example model. As per the assumption, the resistance is divided 2 times to match with the current ship condition. Acceleration equals thrust resistance / ship mass m/s2. Integrating acceleration will give the velocity in m/s. Integrating the velocity further will give distance traveled by the ship in m. Inputs used. Gearbox reduction ratio equals 2.06. Engine inertia equals 1.61 kg/m3. Ship weight equals 32,000 kilograms. Propeller diameter equals 620 millimeters. FTP data available for torque. Point 2 engines are present of same configuration. Engine 4 GDA_170 HP at 2000 RPM inline. B. Assumptions. Resistance map is scaled down as the data available was for bigger ship. Fuel map used is dummy map. Resistance data is based on the example model. C. Input graph. Since the full load data was available, so the torque data at 0% load is assumed. Fuel consumption graph is dummy graph taken from GT example model, so the fuel consumption results cannot be correlated with the actual results. FMEP data was not available, so it was ignored while building the model. D.GT Suite model. Modeling in GT Suite is done by using various controller and switches. Since GT has a vast library of different controls, the modeling of equation is easy part. Once this equation is modeled in GT, then connection has to be established to make a flow path. Flow should start from the engine and the feedback should to given back to the engine. Feedback signal receives the signal from the thrust and the input velocity profile given to the driver controls. Here only forward cursing of the ship has been modeled. Accelerator input is based on the speed input given. 4. Results. A. Velocity. Test data is in correlation with the simulation data. B. Ship speed and engine speed. Here the engine speed is below the idle condition, idling speed is above 600 rpm, but after 300 sec we can see that engine is responding in reference to the vehicle speed. C. Ship speed and fuel consumption. This graph is only for reference purpose, as the fuel consumption map used is dummy map as referred from Ricardo model. Once test fuel data is available, so fuel consumption can be predicted accurately. D. Clutch engagement. Clutch is engaged throughout the cycle. E. Power. Max power obtained is 122 HP at 600 SEC for 1527 RPM. Torque. Max torque obtained is 570 Nm at 600 SEC FOR 1527 RPM. Torque. Max thrust obtained is 45,561 N. Distance traveled. Distance covered for the given ship travel is 2 km. Conclusion. Able to perform ship modeling in GT Suite, results are comparable with real case scenario. From the results is can be observed that the results variation for thrust, velocity, and distance are within plus or minus 5% range. With proper engine map and measured ship resistance data, the results can be improved, which will result in less error in simulation result. Hence, if proper fuel economy map is provided, it also can be predicted properly. PID controllers are used to convert the equations to the executable format. Literature study has helped in this simulation for modeling of different equation used to control the ship architecture. Acknowledgement. The author would like to thank 1. Dr. Ravi Damodaran, Chief Technical Officer, Research and Development, Greaves Cotton, for his guidance throughout the project and his vision in building team with simulation capability. 2. Mr. Emil Recker, Sister GM, Power and Industrial Engine Department, Greaves Cotton Limited. 3. Mr. Rajendra Chandola, AGM, Application Engineering, Greaves Cotton Limited, for giving the opportunity to work on this project.